Welcome to the first real lesson of the course, entitled Control Theory. I will be upfront with you. There's a lot of information in here. If you are like me, it is relatively easy material to grasp as you work your way through it, but even easier to forget. Not the ideal first lesson to have for a course, but logically it only makes sense to have it here. There is a lot of terminology and concepts included in this presentation. Most of these terms will be used throughout the rest of the course. Other terms presented here will not be used as they are mere substitutes, but are included here as they may be used by others in the industry, and it is important that you know them. Because of all of this, you may need to revisit this presentation, or at least parts of it, as you work through the remainder of the course. Additionally, to assist you in keeping this information straight, be sure to print off the HVAC Control Systems course manual and keep it with you as you work through the lessons of this course. In that course manual, you will find a glossary of all the key terms presented here. The objective for this lesson will be for students to comprehend basic control theory. The corresponding samples of behavior will be: list the functions of HVAC systems, define manual control and identify its limitations, define automatic control and identify its benefits, describe the components of both open and closed control loops, distinguish between open and closed control loops, provide examples of common measured variables, control variables, and sensors used in HVAC control systems, and identify the components of a stat. Let's start by looking at this from the 30,000-foot perspective. Why do we need HVAC systems in the first place? Obviously for thermal comfort, but these systems are also there to support various processes, protect equipment, and ensure appropriate air quality. So why do we need HVAC control systems? We could just use HVAC systems that can't think for themselves and use us humans as the controller, turning them on and off as needed. We already do this at times with things like unit heaters, window AC units, or even for the thermal comfort control in your car. This is called manual control, and it will be discussed in greater detail here in a minute. But to do this for all the HVAC systems we encounter could be very time and labor intensive. Having automatic control systems, the ones that can think for themselves, incorporated into our HVAC equipment arrangement provides for convenience. Additionally, automatic control systems have the ability to control for better system efficiency than we could, provide more consistent results as we are prone to get distracted, and provide protection to both occupants and equipment that we could not. Think of the control of fire dampers to starve a fire of oxygen, or chillers turning off to prevent a coil freeze-up when it realizes low pressure in the refrigerant. I would prefer an automatic control system handle these tasks, as I may not be present or conscious to activate such dampers during a fire, nor is my pressure sensing skills on par with that of the sensors those chillers come equipped with. You may have heard terms like pneumatic, electric, electronic, or direct digital controls. These are various types of technologies control systems can use to perform such automatic control, and they are classified by the way in which they transmit information between components of the system, as well as how those components are powered. And the lines are a bit blurred between them. We will discuss these types of systems later on in this fundamentals module. For now, let's dive into some control theory terminology. The first thing we need to define is that of the control loop. There are two types of control loops, closed loop and open loop. The closed loop is probably the easiest to understand and is far more prevalent in HVAC systems. So let's start with that one. Before I show you some fancy diagram distinguishing all the components of this control loop, let's run through a quick example to set the stage. The Montgomery and McDowell text defines the closed loop as a control loop where the sensor is measuring the value of a controlled variable, providing feedback to the controller of the effect of its action. That definition might be a little too much detail for this point in the course, but the key term here is feedback. Take, for example, the driving of a car. Say you want to go 55 miles per hour. In order to maintain this speed, you're constantly adjusting how far you are stepping down on the throttle. If you start to go up a hill, your speedometer will show you that your speed starts to drop below the desired 55 miles per hour. In an effort to stop this slowing down, you step on the gas and the car starts to speed up. Once you reach the crest of the hill, you may begin to exceed 55 miles per hour. thus you back off on the gas a little bit. You're constantly getting feedback from your speedometer, which is a result of your previous actions, stepping on the gas, backing off the gas. This is an example of a closed-loop manual control, because you are part of the control system. It is you who recognize the deviation in speed from 55 miles per hour, and it is you who adjusts the throttle position accordingly. All of this monitoring of the speed and adjusting the throttle can be inconvenient, however. You may get distracted and not be able to maintain that consistent of an output speed. Thus, for longer road trips, you may choose to implement an automatic control loop, cruise control. Now the disturbances, hills, wind, etc., which will cause the change in speed, will be detected by the car's cruise control, and the throttle will be automatically adjusted to maintain that 55 mile per hour set point. Both situations described here are closed loop control, because there is a consequence to the adjustment in the throttle position, and that consequence is realized by the speedometer. The speedometer tells the controller, whether it be a person or a device, what's going on. That is where the feedback is being provided, and then the controller adjusts accordingly. Here's a diagram of such a closed loop. Let's walk through this starting with a device called the controller. It is fed two pieces of information, the first being a set point, and the second being a sensed variable. The sense variable is at times called the control point, but that terminology will not be used in this course. We will stay consistent with referring to this signal as the sense variable for the remainder of the course. The job of the controller is to compare the sense variable to the set point and decide what to do. Again, the controller can be a human making these decisions, in which case we would call this closed loop manual control, or it can be a device making these decisions. In the latter situation, we would refer to this as closed loop automatic control. Based off its decision, the controller would send a command to the controlled device. This command is often referred to as the control signal, as it is denoted here on the schematic. In the car example, the control device would be the throttle. The control device typically is something that moves and thus requires some force. In manual control, that force could come from the human, as it did in the car example. Such a force was applied to the throttle by your sculpted leg muscle. In automatic control, it needs to come from somewhere else. The ways in which we provide that power will be explained in later lessons of this fundamentals module. Often, but not always, there is an actuator between the controller and the controlled device. This is the piece of equipment that converts the control signal into a force. The controlled device is then adjusted, and such adjustment will have some effect on what we call the process plant. That adjustment is often referred to as changes in the manipulated variable. In our example, the control device would be the throttle, the manipulated variable, the amount of gas physically being fed to the engine, and the process plant would be the car engine itself. As the process plant, or engine in this case, ramps up or down, it is going to change the speed of the car. The speed of the car would be identified here as the controlled variable, as that is the variable that is being controlled. In this course, you will often hear us refer to this as both the control variable as well as the controlled variable. We mean the same thing. Most literature uses controlled, and I feel that is probably the most correct term. However, we do use control and controlled variable interchangeably throughout this course. This sensing element measures what we call the measured variable. This device is also called a sensor, and we will use those terms interchangeably throughout the course. In a closed loop, the control variable and the measured variable are the same thing. That's what allows for the feedback to the controller. That is not always the case, as we will see here when we discuss open loops in a second. In our current example, the sensing element is the car's speedometer. Again, the output of the sensing element that is reported to the controller is called the sensed variable. If the sensor is not accurate, the sensed variable will not exactly match the measured variable. Said another way, the speedometer will not be reading the actual speed. So to review, the sensor is the eyes and the ears. They sense something and pass on that information to the controller, which can be thought of as the brains of the operation. the controller compares the sensed variable to some set point and decides what action needs to take place, and then it sends a command, termed the control signal, to the control device. The actuator and/or control device take that command and do something about it. They are the muscles that adjust something in the system to change how the system operates. It should be clear that this is a continuous loop. There will be a constant comparison between the sense variable and set point. Adjustments being made will in turn affect the controlled variable. Such changes would be sensed by the sensor. That information is relayed back to the controller, and the process starts all over again. Now, all of this control theory we are discussing thus far can apply not only to cars, but to anything, including HVAC systems. So let's look at an HVAC example and identify the parts of the closed loop. This diagram here is a very common control configuration in HVAC systems, as we will see repeatedly in the weeks ahead. Relatively cool air is brought across a heating coil. For this example, let's say that we have hot water running through this heating coil. The air warms up as it flows over it. For our system, our intent is to maintain the discharge air, which is the air coming off of the coil, at a prescribed temperature set point. We do this by measuring that air temperature and adjusting how much hot water is flowing through the coil accordingly. So let's identify some of the components of the control loop. First off, what is the control variable? That would be the variable in which we are trying to control for. Thus, it is the discharge air temperature. This is a closed loop. Thus, the control variable is also the measured variable that the sensor is measuring. The sensor, a temperature sensor in this case, measures the temperature and reports it to the controller. That input to the controller is called the sensed variable, and it can be slightly different than the measured variable. For instance, say the discharge air temperature suddenly rises from 90 to 91 degrees Fahrenheit. The measured variable would be 91 degrees Fahrenheit, but since it takes a little time for the sensing element to warm up, its outputted sensed variable will take a little while before it actually reports that 91 degrees Fahrenheit. The controller is pretty obvious. It reads the sense variable and compares it to a prescribed set point. Any deviation between the two, which is often referred to as error, results in an action being taken. The controller decides what to do and sends a command to the controlled device. In this case, the controlled device is a two-way control valve that has an actuator attached to it, which will adjust the position of the valve, that is, how open or how closed that valve is. The resultant amount of water flowing through the coil will be the manipulated variable. The heating coil assembly, in this case, would be what we previously defined as the process plant. A drop in discharge air temperature to a value below the set point would result in the controller telling the valve to open further. The actuator will provide the force to open the valve. More water will flow through the valve and thus through the coil. More heat will then be transferred to the air, and the discharge air temperature will subsequently rise. That rise in temperature will be sensed, and the whole decision process will start all over again. That is why we call it a loop. Now, there are control loops out there that differ from this. They differ in the fact that the measured variable is not the same as the control variable. It is something completely different. In all reality, it's not really a loop, is it? But they call it open loop control nonetheless. So how does this loop work? Basically, all of the components stay the same, but there is no direct relationship between the control variable and the measured variable. The keyword here is direct. For an open control loop to have any chance of working okay, there has to be an indirect relationship between these two variables. So let's revisit that heating coil example and see how we could apply open loop control to it. All things will stay the same except for the measured variable. Instead of measuring the discharge air temperature, we are going to measure the outdoor air temperature. We would expect that when the air temperature outside is dropping, the temperature of the air leaving the coil would be dropping as well. In this case, a drop in air temperature would trigger the controller to decide to allow more hot water to pass through the coil. So where is this so-called indirect relationship between the measured variable, outdoor air temperature, and the control variable, discharge air temperature? Well, if the air entering the coil came directly from outside, as would be the case in a dedicated outdoor air system or DOAS, then it would make sense that a sudden drop in outdoor air temperature would be representative of a sudden drop, albeit a different amount, in discharge air temperature. But this indirect relationship could get even more difficult to predict. Imagine if the air entering the coil is not coming from outside. Rather, it is being recycled from the spaces being conditioned. The control variable would still be the discharge air temperature off of the coil. A drop in outdoor air temperature would mean increased heat loss from the conditioned spaces to the environment, and thus a slight drop in the temperature of the air being returned to the coil, which in turn would affect the temperature of the air leaving the coil. But that is a long chain of events, and quantifying the relationship between changes in outdoor air temperature to the resultant changes in discharge air temperature coming off of the coil would be a very hard thing to do. Though a drop in outdoor air could affect the resultant discharge air temperature, so could changes in occupancy, whether or not equipment and lighting in the spaces are running, as well as how much sunlight is penetrating through the space's windows. The indirect relationship between the measured variable, outdoor air temperature, and the control variable, discharge air temperature, is becoming more and more difficult to define. Keeping the discharge air temperature exactly at set point would be all but impossible. That is why open control loops are rare in HVAC systems. If you are going to pay to install an outdoor air temperature sensor, why not just put it on the discharge air coming off of the coil, where we know there's a direct relationship between measured variable and control variable, because they are the same thing. There are select few instances in which we will see open loop control logic being implemented in HVAC systems. One example would be to control baseboard radiators along the exterior wall based off of the outdoor air temperature. These radiators may not be sized to meet the entire heating load of the space, but are rather there to create a thermal blanket of sorts between the inside and outside. A separate ducted system may be installed to modulate to meet the heating demand of the space. In this case, the radiators may be controlled by an open loop control logic in which the measured variable is the outdoor air temperature. A more common implementation of open loop control logic would be instances in which it is used in conjunction with a closed loop. Here, the output of the open loop controller is a signal which adjusts the set point of a separate closed loop. Let's go back to the heating coil example one more time. Say it is being controlled by a closed loop, and the set point for the discharge air temperature is 90 degrees Fahrenheit. Well, that discharge air temperature might suffice if it's 30 degrees outside. But what if it drops to 10 or less? It may be beneficial to increase the temperature of the discharge air, as the heating requirements of the space receiving the hot air will increase. So instead of sending the occupants 90 degree air, we would send them 100 or even 110 degree air. This concept of adjusting a set point in this manner is known as a reset schedule. And the process of determining what set point should be implemented starts with reading the outdoor air temperature and making that decision via an open control loop. Open loops could be used for other monitoring purposes as well, such as for freeze protection, air filters, or room occupancy. Examples of all of these will be provided in the various lessons throughout the course. In the course manual provided to you, we included schematics for open and closed control loops. Again, I would think it would be beneficial to keep a printed out copy alongside you, as we will be using this terminology throughout the course. We will do our best to keep it as straightforward as possible, but consistently using this terminology will keep the information we are presenting to you organized. Additionally, this is the language spoken in industry, so it is vital you learn how to communicate with others on these topics. Control systems become much more complex than just what you see here. Most HVAC systems have many such control loops which interact with each other, or at times multiple control loops are utilizing the same controller. But the underlying logic will all be based on these elementary systems shown in this lesson. The second module of this course, entitled Control Strategies, in painstaking detail, walks through all the individual control loops seen in a variety of common system configurations, and how these control loops interact with each other. We have defined all of these terms in a control loop, and I know there's a lot of them. But let's give a few examples to kind of hammer home what these various components of a control system might look like in an HVAC system. Some examples of a measured variable would be temperature, pressure, humidity, air velocity, and CO2 concentration. Those such parameters are also examples of what we have for our control variables as well. The corresponding sensing element or sensor could be a temperature sensor, pressure sensor, humidity sensor, velocity sensor, or CO2 sensor. Now oftentimes, the sensor and controller are actually housed together, but they still perform distinctly different functions. The sensors are the eyes and ears, the controllers are the brains. In those instances, when they are housed together, we call such devices stats. A thermostat has a temperature sensor and accompanying controller located in it. A humidistat has a humidity sensing element and associated controller located in it. And I think you can figure out what a pressure stat would contain. Precise control of HVAC systems can be difficult for a variety of reasons. First off, the fact that we almost always are using closed loop control is because things are always changing, which cause deviation in our measured variable from its set point. We call these system disturbances and are denoted as shown here. So what are some examples of system disturbances? Let's again revisit that heating coil scenario. If the inlet air temperature rises or falls, it's going to have an effect on the discharge air temperature. So variations in inlet air temperature would be classified as a disturbance. We could peel the onion back even further and state those underlying causes of temperature fluctuations are also system disturbances, such as increases or decreases in occupancy of the space the air is returning from, the outdoor air temperature, etc. Or the volumetric flow rate of air, that is the cubic feet per minute or CFM, going through the duct could change, as it does in a variable air volume system. That too will affect the discharge air temperature and would be a disturbance the control loop would need to address. You could also have fluctuations in the hot water loop, which would be classified as disturbances. Some examples of that would be a change in inlet water temperature or increased static pressure upstream in the piping system, which would force more flow through the valve than the controller was intending. We have briefly discussed how the sense variable may not exactly match the measured variable, as fluctuations in the measured variable have to warm up or cool down the sensing element before it reports such fluctuations to the controller. This is not the only location where time lag in the control loop occurs, however. Sticking with the heating coil scenario, let's just say initially there's not a large amount of water flowing through the coil. Then all of a sudden the discharge air temperature drops very quickly. Since the sensor has to first cool down, there's going to be a time lag associated with the sensor before it reports this drop in temperature to the controller. Once that information is received, the controller tells the hot water control valve to open, but it takes a second for this increase in water flow to actually enter the coil. Then the coil itself has to heat up a bit before it can in turn start supplying additional heat to the airstream. And what if the sensor is a ways downstream from the coil? There would be an additional delay before we got the feedback that the increase in water flow is actually bringing the air temperature back to set point. All of these collective delays in the control loop response are referred to as the system time constant. The smaller the time constant, the easier the system will be to control. An additional issue which adds to the difficulty of controlling systems would be the concept of hysteresis. When a controlled device, such as a control damper or valve, switches direction of travel, there will be friction and mechanical slack that needs to be overcome prior to actually traveling in the opposite direction. This concept will be discussed later in more detail, but for now just be aware that it adds to the difficulty of controlling HVAC systems. The rate at which a controlled device, again whether it's a damper or valve, moves to a new position is referred to as its slew rate. The controller may tell the hot water control valve shown in the schematic here to go from fully closed to fully open in a moment's time, but it can only travel as fast as its slew rate, further adding to the response time of the control loop. The last major obstacle control systems are faced with is that of gains, both system gains and controller gains. This can be a very difficult concept to explain, and in my opinion is explained poorly in many of the controls books out there. The next lecture will dive into this concept in greater detail. This lesson introduced you to a lot of new terms. The diagrams and terminology discussed here will be revisited often throughout the rest of the lessons, especially those in Module 2, Control Strategies. This lesson will be available to you throughout the remainder of the course if you need to further review it. There is definitely more to control theory, but it is probably more effective to introduce such additional concepts as we encounter good examples of them in the lessons ahead. Again, the lesson objective for this lesson was for students to comprehend basic control theory. The corresponding samples of behavior were to list the functions of HVAC systems, define manual control and identify its limitations, define automatic control and identify its benefits, describe the components of both open and closed control loops, distinguish between open and closed control loops, provide examples of common measured variables, control variables, and sensors used in HVAC systems, and to identify the components of a stat.